today in section 1.6, we're going to look at two of the most common measures of data spread about the data. So one of them is called variance, and the other is called standard deviation. Just by way of review, and you don't have to write this down, we have already seen things like mean, also known as average. We've also seen median, and these are single numbers that attempt to describe the entire thing, right? So if you have data spread out all over the place, and you wanted to know, well, what's the number that describes it all? You might say, oh, the average is this, the mean is this, the median, the middle number is this. So it's one number that kind of describes everything. We also see mode. Mode is a number that describes a lot of stuff. It just says, what's the most frequent piece of data that shows up, okay? Another thing that we talked about was IQR. And besides those, we also said there's the 5-number summary, the 5-number summary. So we've looked at a couple different single numbers that help describe all the data. Well, let's look here. Consider these graphs here. So this is something called women's basketball. And we have the Dolphins here and the Sweet Peppers here. These are just fake things. I actually got this from the book, so don't accuse me of any weirdness, okay? So, all right. So let's look. What I want you to do is to look at the data, and it's going to take you a little bit for step 2, because step 2, you're going to have to find the mean, median, and mode, 5-number summary, and the IQR. And of course, you have to put this in order real quick. So you're going to take these numbers and put them in order, take these numbers, put them in order, then you can calculate it. But real quick with your neighbor, actually, let's just look at number 1 and answer that question. So the Sweet Peppers have a major cluster, and if we look at this data is more evenly spread out.
Can you argue that
What we're going to see is that there is two other pieces of data that would be helpful to analyze, and this is where you start really feeling like a statistician. All right, let's walk through some vocabulary. It's going to take you a while to get used to the X sub 1, the mu, the sigma, because we're going to get into Greek math today. So the first one here, mean. We use, when we are talking about population, people, number of people, etc., we're going to use Greek letters. When we are talking about samples, like the number of rocks or the number of earthworms, so non-human numbers, we're going to talk about and use different notation, which we'll get to here. So we're going to use Greek letters when we're talking about human population. I honestly don't know why that's the case. Okay, so the first one, you can pronounce mean. You can pronounce the Greek letter mu, like a cow. But I've heard it more pronounced mu, like M-Y-U, okay? Mu. All right. And of course, we already know what mu means, or we already know what mean is. This is the average. You add everything up and divide by the number, okay? Okay. Another number that is helpful is called the deviation. And the deviation simply means this: how far away is one piece of data, so we call it datum, D-A-T-U-M, that's one piece. Data is plural, datum is singular. One data, how far away one data is from, and I'll do the Greek letter mu there for average/mean. Sarah. The square of a deviation, because when you square a number, you will always end up with a positive. So why don't we do absolute value? Not quite sure. But I do know that if you square the deviation, you end up getting a positive number. So the square of the deviation essentially positivizes, there's a good word, any number. And it also gives more weight. It gives more weight to farther numbers. And we'll unpack that in a moment. Numbers that are farther away from the average are worth more when you square the deviation. So the square of the deviation. Again, don't forget that x sub I is just the term. So x1, x2, x3, x4, my first term, my second term. So this just says whatever term you have, subtract it from the average, the mean, and then square it. You will always get a positive number, and the farther numbers will give you more weight. All right, variance. Variance this reads sigma. This is the Greek letter sigma. So we say sigma squared. And sigma squared says this. You add up the square of the deviations, and you divide by the number of terms. So how do we write that? It is the sum of not sum. It'll be the mean. The mean of the square of deviation. On the next page, we hear, this is probably the most common phrase you're going to hear, the standard deviation. Standard deviation is just the square root of the variance. So whatever number we get after we take the average, all we do is take the square root. So let's walk through these data points and look at the Dolphins' team heights. We're going to calculate what the deviation is from the mean. So each one, how far away from the mean it is. Then we're going to take those squares, write them down. Now what we have to do, remember, is that we have to add them all up. And then we have to take averages and also take a square root. So it's going to sound complicated, but it's completely doable. All right, so squeeze in 80 there, or on the side. We do have to add everything up, so that's why I'm keeping it on the table and not just throwing 80 over onto the side. There. Okay, first off, we need to find out what the average, remember that's called mean. So what's the average of all this? Well, we're going to add up all of these numbers and divide by 10. So I see that my total, the sum, is going to be 750. I do apologize for squeezing it in there, but I'm going to write it underneath on the bottom. That's where my sums are going to be. So I take the 750 and I divide by 10. So my average is 75. Now we're going to use that mean for the next few steps. What we have to do, finding the deviation, is I'm going to take the 70 and I'm going to subtract the mean, and in the end I get -5. -5. So the deviation, the negative tells me it's under, the 5 means it's 5 away. It's 5 inches away from the average. So when we square that, we get a positive 25. I'll do 71 and keep going, and then from there you can just jump ahead. So here, when I subtract the 2, I get -4, and when I square that, I get positive 16. So go ahead and work through that. All right, so now that we filled it in, we have all the differences here. So how far away from the average is each player? So only one player is exactly average. So nearly half the data is up there, and nearly half the data is under there. So most people are, you can't even say most people are above average. Now we have to find out what the variance is. So if you recall what variance is, add up all the squares. So we're going to add up all of these numbers. And again, I didn't leave a lot of space there. My apologies. And then we're going to divide by the total number, which I believe there are 10 players on the team. So, all right, so we added up all the square of deviations to get 128. So that's the 128 here. And we are going to divide by the total number of items, or the population in this case, with 10 players. So here we get exactly 12.8. Now the standard deviation is just the square root of that. We take the square root of 12.8. 3.6. So, how do we represent this on a graph? How do we represent this on a graph? Well, let's look up here. We know that the mean, we already know that the mean is 75. So, here is the mean, is 75. And we know the standard deviation, sort of like the wiggle room for the data, is just under 4. So here it goes to 79, so somewhere about here. And this goes to just about 71 there. So this would be your sigma. So what it tells us is that the data is spread out quite a bit. And look, the data is spread out quite a bit. We see that it is almost normal all across the board, spread out pretty well. As compared now to the other situation. As I said yesterday, when we are talking about population, we use Greek letters. And when we're talking about a non-human population, so a sample of rocks, a sample of earthworms, which we'll look at momentarily, then we're going to use slightly different notation, but it means the same. So here, we're going to say x with a bar, so you just say x bar. That's the mean, x bar. I don't like using s's because they look like a 5 when I write them, but s squared is the sum of the squares. Is your variance. And then, of course, your s is just going to be your standard deviation. Take a gander at the formulas. And what do you notice? What do you notice that's different than the previous situation? So a key thing to pay attention to is n minus 1 is slightly different. Now, it turns out that when you're doing population, you might also use the n minus 1. It's sort of a debated thing. Which number gives it better? When I divide by n, the number of samples, or divide by n minus 1, because what that would do would give you a larger spread, which could incorporate the data even better. So it's kind of a debate. So one is sometimes used, one is the other one used. So the question, of course, is what will you use? And so generally speaking, we're going to use this as our default formula with the minus 1. Okay, there's also something some of you may have noticed, and I think it's a little bit confusing right here. What does this say right there? Does it say subtract first, then square, or does it say square and then do subtraction? Right, so I would argue that we probably should subtract first, then square.
But that's not the order of operations.
True. What they meant to communicate, though, is that you're supposed to take the square of the difference, not the difference of squares. So now let's continue this journey. What we want to do is find the averages here. So the sum, of course, the sum here is 90 when we add up all the worms together. And therefore the average is approximately 12.86. And I'm going to put the approximate symbol there for our mean. And now just to show you, remember that we're doing 4 minus the average to get our approximate value. And I'm going to tend to round things to the hundredths, and then I'm just going to fill out this chart real quick. So here I filled in the data. Again, I subtracted the item and the average here. Notice that some of my numbers are negative and some are positive, and when we add them together we expect a 0. We expect all of these to add up to 0 because the difference, some of it is under, some of it is over, but it all averages out to this. Alright, so now we square each of these. So notice that the larger looking differences, this one it has an 8.9 distance, it is weighted so much more. This is a 10.1, so it's weighted very much. But this one right here is as a very small difference, so it has not much weight on the square of deviation. So this is kind of like a weight. It provides more weight to the larger numbers. That is, the numbers that are farther away from the mean. Okay, so now standard deviation, and in this case, or excuse me, variance is going to be s squared. So let's just remember what we do. We take the sum, and we're going to sum of squares here, and we're going to divide it by n minus 1. So that's the important part. I'm not going to be dividing by 7 squares. Here I'm going to be dividing by the 6. So the 244.9 divided by the 6 is going to approximately be 40.8. So that is our variance, 40.8. Now our standard deviation is all we have to do is take the square root of that to get 6.4. So if our average number of worms, is almost 13, the standard deviation is 6.4, which means that the spread goes quite a bit up, so 50% more or 50% less.